Okay, so it's my pleasure to introduce Kostas Daskalakis, although he needs no introduction. Uh, he's a professor at MIT ECS, and he has done groundbreaking work in a variety of fields, especially my favorite, Nash theorem computation. I'm a fan of it. That basically kickstarted AGT field. Um, this work he did when he was at UC Berkeley doing his PhD with uh, Christos Papadimitriou. After that, he worked on complexity of multi-item auctions, which was basically kind of follow-up work that kind of extended the work of Myerson in a big way, uh, and on single-item auctions. And after that, more recently, he has jumped into machine learning. So he's interested in doing high-dimensional and statistics and machine learning for strategic data. He has won numerous awards. I'll just list a few. Novelina Prize, ACM Doctoral Dissertation Award, Kalai Prize, um, SIAM Outstanding Paper Award, Sloan Fellowship course, and so on and so on. So without any further ado, I'll hand over to Kostas.
Thank you so much, Ruta, and thanks to everybody for being here. I'm probably not gonna be monitoring the chat, but I'm gonna make some stops, and please feel free to unmute yourself and ask the questions at those points. But yeah, so it's
the chat, and I can probably tell you.
Awesome. Yeah. That's great. So I actually hear some background noise. I wonder if people can mute themselves. Yeah. All right. So yeah. So it's a pleasure to be here. As Rita mentioned, I had been doing a lot of work on complexity of computing equilibria in the past, and more recently, I've been interested in machine learning. And these days, there are some exciting opportunities emerging in the interface of these two fields, as learning systems are becoming more and more interconnected. And today's talk is about exactly that. So one motivating question for this talk is the following. So on the left is a photo of AlphaGo, an algorithm playing against the human champion in Go. And as you know, AlphaGo is beating the human champion. On the right-hand side, you see a video of a Waymo car which is trying to enter a highway, but is being antagonized by human drivers, so much so that it aborts the attempt, exits the highway, and tries again. The question I want to ask is, how is it that machine learning models can beat humans in very complex games like Go, but might have a hard time playing easier games that most people can play reasonably well? And just to put a broader perspective on this question, I'd like to summarize the exciting progress that has been made in deep learning in the past decade in this picture, which tries to succinctly describe our ability to train very complex learning models by simple methods like gradient descent. So a lot of the progress in deep learning is due to the fact that we can write very, very complex models and train those models using data with very simple procedures that are computationally light. Of course, that's not the full story, we have made a lot of progress in choosing the right complex models. We've also made progress in collecting a lot of relevant data to train these models on, as well as we've made a lot of hardware innovations in order to be able to train complex models over a lot of data. But in terms of the training itself, an empirical finding that has been driving this approach to deep learning has been that even though when you train these very complex models, the optimization landscape that you're facing is very complex, nevertheless, gradient descent or gradient descent variants tend to arrive at local optima that generalize well. So they do a good job in terms of the underlying learning application that you're trying to solve. So yeah, the optimization landscape that you're facing when you're trying to train those learning models is going to be very complex. Nevertheless, simple methods like gradient descent will arrive at local minima, local optima that do a reasonably good job in the learning task that you're trying to solve. So back to my motivating question, the challenge that we will face now, we are already facing, and we certainly will face down the road, is that our complex learning agents are not going to be in some environment by themselves. Instead, they're going to be all learning and taking actions in the same environment and interacting with each other in that environment. So the pertinent question is, what type of learning and optimization technology should we endow our models with? And the unfortunate empirical finding here is that if each of these agents who are, again, learning and making decisions in the same environment, they all run their own separate gradient descent procedure, the dynamics of the system have a very hard time converging, let alone to some meaningful solution. So the question I want to understand in this talk is, how deep is this issue with non-convergence? And that's important because if we want to generalize what has been happening in the single agent learning applications to multi-agent learning applications, we better understand what type of optimization procedures we should be using in those types of applications. And as I said, the practical experience is that gradient descent isn't converging. So let me show you some examples of that. And for the examples that I'll show, and for the remaining of the talk, I'm going to focus on one very special case of multi-agent learning, which is two-agent adversarial learning, which is summarized abstractly by a min-max problem of this form, where you should think of f as a non-convex function, and you should think of x and y as high dimensional. Although the exact setting that I'm going to be talking about will vary, and I will make the context clear in different slides. Now, the method of choice that people use to solve these kinds of problems, if x and y are high dimensional and f is non-convex, is to have the min player and the max player run their own gradient descent procedures. Of course, because x is the minimizing player, he's running gradient descent, and because y is the maximizing player, she's running gradient ascent. So one strategy, one approach to solving such a problem when x and y are high dimensional and this is non-convex, is to have these two players run gradient descent in parallel. You could also run some variant of gradient descent. Okay, but this is what people have been doing, and they have found empirically that it's a very difficult problem to solve. And let me give you some pictures of the types of things that go wrong when you try to do that. Both of these pictures are going to be from training GANs, so training generative adversarial networks, which I'm not going to get into in detail because it's not super relevant for the talk. But think of a GAN as a min-max formulation whose goal is to come up with a generative procedure that is generating items from a particular target distribution. So what you see in this first example is training a GAN on the dataset called MNIST that contains handwritten digits like the ones you see here. So here you have a 10 modal distribution over handwritten digits. And in this panel over here, you see what things the generator of a GAN generates if you run gradient descent ascent to train it and you stop it at different steps of training. As you see, the generator is failing to generate the target distribution. It's generating garbage symbols until eventually settling to a unimodal distribution over some other garbage symbols. So that's one example of GAN training failing if you run gradient descent ascent dynamics. And here's another one in a simple distribution. So here the target distribution is a mixture of Gaussians whose means are arranged around the cycle. And again, here I'm showing what distribution the GAN is generating if you stop the training at different steps. As you see, it's generating points from different mode of that multimodal Gaussian mixture. So these are two examples, two practical examples where solving min-max problems fails. And again, what GANs are is not important for this talk. Let me show you the simplest ever example where gradient descent ascent dynamics fails to converge. And this is for this trivial function here, where x is a scalar, y is a scalar. In which case, the gradient descent ascent dynamics degenerates to this iteration that I'm showing you here. So the minimizing player is running this update, while the maximizing player is running this update in parallel. So for this simple function, it's very clear that the unique min-max equilibrium is this point here, the 0, 0 point, because unless both x and y are 0, the other player can punish them infinitely hard, right? So if x is 5, y can set itself to plus infinity to collect plus infinity reward in this zero-sum game. Similarly, if y is non-zero, x can set itself to punish y infinitely much to make the function minus infinity. So the only equilibrium is 0, 0. Nevertheless, if you run gradient descent ascent, say starting from this point, the trajectory of gradient descent ascent is spiraling away from the equilibrium. So that's the simplest possible case where gradient descent ascent fails. And it's important to note this case because, I don't know, I mean, in the previous slide, who knows what function f is used here and here. It's a non-convex, non-concave function, but this function is a very simple one. It's a bilinear function, and in particular, it's convex in x and concave in y, which is the dream type of function for a min-max problem. It's exactly the setting that von Neumann studied in his 1928 paper. So this is the dream scenario for a min-max problem. And even though it's the dream scenario, still gradient descent ascent does not converge. And what I want to do in this talk is I want to understand why these things are happening, why gradient descent is not even settling at approximate local or local min-max equilibrium. Okay, so training oscillations, to summarize what we've seen so far, training oscillations and garbage solutions arise in gradient descent ascent dynamics even into agent zero-sum settings, even when the objective is convex concave, like the x times y objective, and even if the function is perfectly known. So of course, so it is happening for these simple scenarios. Good luck when your objective function is non-convex, non-concave, and when the function needs to be learned as well as be optimized, as is commonly the case in machine learning settings. So I want to dive deep into what is happening here on this front. And our focus is going to be a comparison. So I want to compare minimization problems, which have been driving developments in deep learning in the past decades, and min-max optimization problems that are encountering these issues that I've described in the previous slides. So these are the two problems that I'm going to be looking at. And I'm going to be considering these problems when the function in the left-hand side, in both cases, the function is going to be Lipschitz and smooth, which means that its gradient is Lipschitz. And I'm going to take set S to be a convex and compact set. So under these conditions, both problems are well defined. So they have solutions. And I want to understand the computational complexity of these problems. So let's compare the problems. And I want to compare these two problems in the in the innocent, in the early years, in the modern times. Okay, so in the early years, when people were looking at problems like these, they were considering f's with particular properties. I've already said that the dream type of function for a min-max problem is one that is convex in the minimizing argument and concave in the maximizing argument. As the dream case for a minimization problem is when the function is convex in its argument. If it was maximizing, then the dream case would be concave. So what do we know in these special cases of the problems of interest? Well, in terms of complexity, and in particular, performance of first-order methods, these problems behave very similarly. So if you're trying to solve a minimizing problem for a convex function f, then a classical result from optimization theory says that first-order methods find approximate minima in a number of steps and queries to function f and its gradient that are polynomial in the approximation, the smoothness of the function, and the diameter of the set you're optimizing over. And exactly similar statement also exists for the min-max setting if f is convex concave. No real difference between the two problems in their corresponding benign settings. And just to be clear about what I mean, approximate minima and approximate min-max, well, I mean the natural thing. So an approximate minimum is a point x star that cannot be decreased by more than epsilon by switching to a different point. Similarly, an approximate min-max equilibrium is a point x star y star such that you cannot change x to decrease the function by more than epsilon. You cannot change y to increase the function by more than epsilon. So if you're targeting approximate minima or approximate min-max equilibria, in these benign cases of the corresponding problems, the complexity is not very different. So you can do that using gradient descent type of methods in a number of steps and queries to the function and its gradient that is polynomial in the relevant parameters. So there's not real distinction between the two problems in their benign settings. So, The training then oscillations that I showed for the function x times y, which was a special case of this problem, is not due to computational intractability, but it is a feature of the training procedure that I was running in that figure with the spiraling out behavior. Okay. So, but it's not reflecting intractability in the problem. It's really a choice of the method that I'm using. It's a reflection of the method that I'm using. And one question is, can they be removed? Can those oscillations be removed? And notice that these theorems don't say anything about kind of like what type of convergence the methods have to the min-max or the minimax, right? They only say that there are procedures that can compute for you an approximate minimum and an approximate min-max equilibrium. They don't tell you whether you have last iterate convergence or some other type of convergence to the solution. All right, so that is kind of like the picture for the easy settings of these two problems. But modern times are considering the complex case of these problems, which on the left-hand side correspond to a function f that is not necessarily convex, it is just Lipschitz, and similarly a function on the right that is not necessarily convex concave, but is just Lipschitz. So what can we say in this case? Well, the TCS perspective is like, what are you even trying to do, right? I mean, it's simply hard to find to solve these problems. If your function here f is non-convex, then the problem becomes NP hard. And a fortiori, if you have a min-max problem, that's at least as hard as this. So that's also NP hard. So what the heck are you trying to do? Well, the deep learning community has been saying, look, I don't care if the problem is NP hard. Just go for a locally optimal solution. So what we want to understand in this talk is, what's the complexity of locally optimal solutions? And is there any inherent difference between minimization and min-maximization? So let's try to compare again. First, what is a locally optimal solution here? It's a natural thing. You're looking for a point x star, so I'm going to call it epsilon delta local minimum a point x star, such that if I move in a delta neighborhood around this point, I cannot decrease the function by more than epsilon. So that is a natural notion of local minimum. And similarly, a natural notion of local min-max equilibrium is a point x star y star, such that I cannot locally change x star to decrease the function by more than epsilon. I cannot locally change y star to improve the function, increase the function by more than epsilon, where locality in all cases means in a delta radius around the corresponding points. All right. So if I now settle for this type of approximation and local approximate solutions, how do these two problems fare? Well, on the left-hand side, as it turns out, if your delta radius in which you're looking for deviations is not too large as a function of epsilon, the approximation, and L, which is the smoothness of the function, the picture stays as it was in the easy case. So again, first order methods can find such approximate local minima in a number of steps and queries to the function and its gradient that are polynomial in the same parameters. Okay, and the only difference with the previous result, which applied to when f is convex, is that now I have a constraint on delta, on the locality in which I'm looking for improvements, and that's necessary, right? Because for larger deltas, while epsilon delta local minima still exist, the problem becomes NP hard because you're now looking for global deviations around x star, and whenever your function f isn't convex and you're looking for global deviations, you're facing NP hardness. But the theorem says that if delta is appropriately restricted, then first order methods can still deliver for you a local approximate minimum. All right, so, and this is what's been driving deep learning. So yeah, globally optimal solutions cannot be found when f isn't convex, but local approximate solutions can be found. And in practice, these are okay. These are good solutions. What happens on the right-hand side if I target epsilon delta local min-max equilibria? Well, the first thing you can prove is that existence of solutions still holds if delta is restricted in the same way. Okay, so for larger deltas, these things may not even exist, but you can show that if delta is appropriately restricted, these solutions do exist. So that's a reasonable target for optimization procedures. But what is very unclear is what is the complexity of finding them. And because this is unclear, in these types of scenarios, the training oscillations we have been encountering could be either a result of intractability, as well as a result of the types of procedures that we're using for these problems. So now we have an either or. In the convex concave case, whenever we see oscillations, these are due to the type of method that we're using and potentially can be improved with a better method. But over here, when the function f is not convex concave, the training oscillations that we have been finding in practice could be due to either some intractability that underlies this problem, or it could be that we're not using the right method, but potentially different method could deliver us some stability and computation of approximate minimax equilibria. So this is sort of like the first segment of my talk, trying to set all the problem statement and all the constraints around it. Are there any questions about what I've said so far?
So I'm just curious about what training method you use for the oscillation case for fxy, where xy equals,
Yeah, so,
I mean fx.
Yeah, so I used exactly the vanilla gradient descent ascent. So exactly the dynamics that I wrote here. I used exactly this method. And one reasonable question is, what happens if I add bells and whistles to this method? Like, momentum, another type of thing people do is to have one step of x for several steps of y. Put penalties on the size of the gradient to, disallow the dynamic from escaping too far away from zero. So you can add a lot of bells and whistles, but as it turns out, these, none of them removes the oscillations. So I can show you pictures later maybe in the, where, even for bilinear objectives, adding all sorts of bells and whistles cannot remove the oscillations that you see here. Yeah, so.
Thank you, Kostas.
Yeah. Yeah, so let me move on, and please interrupt me at a later stage if there are questions in the chat or somewhere else. Okay, so again, so I want to revisit the two settings of interest, convex concave and non-convex non-concave, and revisit the question of, can these oscillations be removed? And as I said, in the convex concave setting that I'm going to consider now, oscillations are not the result of underlying intractability, but they're the result of the methods that people commonly use to solve these problems, and I'll try to remove those oscillations somehow. Yeah, so what do we know about convex concave settings? Well, the most fundamental result here that I'm sure you all know is von Neumann's Minimax theorem. states that if f is convex concave and continuous, and these sets, constraint sets are convex compact, then min max equals max min. And this has been generalized a lot to related settings, but it's not a full, like it does not hold in general if f deviates significantly from convex concavity. Moreover, you get a lot of other structure from von Neumann's theorem and related results in the optimization literature. You know that the min-max point is essentially unique. Certainly, the solution space is convex, and the value, the optimum, is always unique. So here's just a simple example of a saddle point. And further, the Minimax theorem is intimately related to convex programming duality. So in particular, the statement of the Minimax theorem is equivalent to the statement of strong convex programming duality. And moreover, min-max equilibria can be computed via convex programming, and vice versa. Any convex program can be solved by casting it as a zero-sum game with a convex concave object. So something else is very interesting, that a sequence of work starting in the 50s and still being a very active area in learning theory show that in this convex concave setting, if the X player if the players play over multiple rounds and the X player uses any no-regret learning algorithm of their choice to update their strategies XT, while the max player is also using any no-regret learning algorithm of her choice to update Y, then the joint behavior of the players converges to a min-max equilibrium. And this is a great result because there are many no-regret learning algorithms like multiplicative weights update, follow the regularized leader, follow the perturbed leader. Even gradient descent is one of them, is a no-regret learning algorithm. So what this theorem says is that if the min player is running any no-regret learning algorithm of their choice, while the max player is running any no-regret learning algorithm of their choice, the joint behavior will converge to min-max equilibrium. So that sounds great. But what I want to understand is what convergence means in the context of this theorem, because it seems to go against our experience with this x times y function where we had oscillation. So as I said here, gradient descent is an example of a no-regret learner. So why is it that no-regret gradient descent oscillates in that example, given that these guys here are saying that it does converge to the equilibrium? So what type of convergence are they talking about? Right? So the type of convergence they are talking about is an average type of convergence. That if I average the trajectory of the dynamics, I converge to the min-max equilibrium. But they are not saying that the last iterate is converging to equilibrium. And here what you see is that the last iterate is actually diverging from the equilibrium. So in particular, the type of behavior, if you want, that is proven in this online learning literature is this type of convergence. This is the same or similar to the convergence of the moon to the Earth. So the moon is going around the Earth. If I average the moon trajectory, it converges to the Earth. But it's not like at any point in time the moon converges to the Earth, luckily, okay? And here it's even worse, right? It's like it's even spiraling away from the target, not just cycling around the target. So how can we improve that state of affairs, which I said in my answer to Ruta's question is very robust, even if you try other variants of gradient descent ascent. Well, let's look into that picture. So, think of this purple thing as a spaceship, right? So the spaceship is getting a boost, it's moving to another point, getting another boost. So what this picture here implies is that the spaceship has bad momentum. The momentum that it has, it's pushing it away from the target planet, which is here. So when you have a spaceship with bad momentum, it is reasonable to try to correct that bad momentum. And sort of like a few years back, we proposed for training GANs, but as well as convex concave functions, we proposed the use of what is called optimistic gradient descent ascent, which undoes a little bit of yesterday's push every day. Right? So every day you do what gradient descent is telling you to do, but at half the learning rate, which is eta, you undo the push from yesterday. Right? So you add a little bit of yesterday's gradients for the minimizing guy, and remove a little bit of yesterday's gradient for the maximizing guy. And in my picture here, the result of that is kind of like that, you know, you add a little bit of half the negative of this to the current gradient in an attempt to correct the dynamics. And what you can show is that if you do this correction, you will actually get your spaceship to the target. So this is the type of thing we proposed doing a few years ago. And you know, as it turns out, this type of thing, this type of negative momentum of sorts has a long literature in optimization, and in particular, the method we suggested, this optimistic gradient descent ascent, is a case of what is known in the optimization literature as Popov's method, and is related to another negative momentum type algorithm, which is called extra gradient, and which was proposed even earlier by Korpelovich. Now, the details of extra gradient and optimistic gradient descent ascent do not matter for the purposes of the talk, but the point is that, you know, a line of work starting with Korpelovich and you know, going into more recent work has already established that these methods with negative momentum actually have asymptotic last iterate convergence to the min-max equilibrium, as long as the function f that you're optimizing is convex concave, or what is shown in more recent works, or not too far from being or not too far from being convex concave. All right. So these are good ideas, is what this line of work says. Good ideas when you are trying to get last iterate convergence results, at least asymptotically. And sort of like an even larger line of work in machine learning in recent years, including the paper that I mentioned earlier, is trying to identify rates of convergence. Now, these rates have been very well understood when you're solving an unconstrained min-max optimization problem with a convex concave function, objective function. If you're looking for an interesting open problem, the constraint setting is not well understood. So getting last iterate and fast convergence rates in the constrained min-max setting with convex concave objectives using these or other methods is not well understood. And that's a very interesting open question if you're looking for one. All right. And that concludes my short treatment of the convex concave case, where again, the issue with oscillations is not intractability. The issue with oscillations is using the wrong type of gradient descent ascent method. And here I'm giving you two methods that are guaranteed to asymptotically converge. The open question is what the rates are in the constraint setting. The big open question, though, for deep learning in multi-agent settings is, can you get any positive result, last iterate or not, when the function f is not convex concave? And this is the main focus of this talk. So what happens in the non-convex, non-concave case? Remember that in this case, approximate and local min-max equilibria, which are defined as this, as I discussed earlier, exist if your radius within which you're looking for deviations is small enough in comparison to the approximation and the smoothness, but the complexity of the problem is not well understood. In recent work with Stratis Koulakis, who is a postdoc at SUTD, and Manolis Zabetakis, who was my PhD student and he's currently a postdoc at Berkeley, what we showed is that first order methods need a number of queries to f and its gradient that is exponential in the relevant parameters in order to find a local approximate min-max equilibrium. So in contrast to minimization, where you can get positive results if you restrict your attention to local minima, in the min-max setting, first order methods cannot deliver you even local approximate min-max equilibria without paying exponentially many queries to the function and its gradient in at least one of the relevant parameters of the problem. So that's a barrier for first order methods like gradient descent or other variants of gradient descent, which are using only the function value and the value of the gradient. And it's an unconditional result. It is not subject to any complexity theory. Nevertheless, this unconditional result is actually a corollary of a broader machinery which establishes a complexity theoretic result, which says that computing approximate local min-max equilibria is actually PPD complete in this setting where they are guaranteed to exist. And which implies in particular that any algorithm, first order, second order, or whatever, will take super polynomial time to find local approximate min-max equilibria unless P is equal to PPAD. So in the complexity theoretic hierarchy, which shows P, NP, and PPAD, which, as I hope we're all familiar with, has as complete problems finding Brouwer fixed points of Lipschitz functions and Nash equilibria in non-zero sum normal form games. What we showed is that finding local min-max equilibria in non-convex, non-concave zero-sum games is exactly as hard. So it's PPAD complete, and in particular, it's exactly as hard as Brouwer fixed point of Lipschitz functions, Nash equilibria in general sum normal form games, and any problem in PPOD. So this is our main result. And from this main result, I want to extract, before giving you a sort of like impressionistic view of the proof, I want to extract a philosophical corollary in relation to my very, very first motivating question. So remember, what I said earlier is that a lot of the progress in deep learning has been driven by our ability to run simple methods like gradient descent or variants of gradient descent to train very complex models on lots of data in supercomputers. So, the point is that local minima are good. Local minima can be arrived at even if the the function f that we're trying to optimize is non-convex. And this has been driving this progress here. So the corollary, philosophical corollary of the work that I showed you in the previous slide is that because local min-max equilibria just cannot be computed, generally speaking, there are these intractability barriers, both unconditional and conditional. My view is that to make progress in multi-agent deep learning, we need to do a lot more work in terms of modeling the game theoretic scenario or learning theoretic scenario that we're trying to, multi-agent learning theoretic scenario that we're dealing with, we need to decide what are the useful and reasonable solution concepts in the setting that we are studying. We need to learn a learning model that has the right inductive biases and which could potentially be fertilized by opinions of domain experts. And we need to design the learning and optimization algorithm well. So, in other words, you cannot just have a blanket general framework that applies to any multi-agent learning scenario right off the bat. You must do a very good work in designing your learning model to have the right inductive biases. You need to design very well your optimization algorithm to arrive at your desired solution concept. And this type of thing can only happen with domain knowledge. And this is why I think this talk is relevant to this community, besides the connection to complexity of computing equilibria, because you are a group of domain experts in multi-agent settings of different types, and you have to decide how to formulate your problems, your solution concepts, your inductive biases to deal with your applications, okay, if you want to use deep learning models. And I think only if we and you and everybody does that, we might be able to get more successes like the AlphaGo algorithm that I showed in the beginning, because what's important to note there is that developing that algorithm was not just, like writing down a model and blindfoldedly doing gradient descent on that model. Actually, understanding what model to write down, how to structure it, and so on and so forth, used a lot of game theoretic knowledge. In particular, it used understanding of what types of algorithms should be used to solve turn-based, deterministic, complete information zero-sum games. Okay, so that is the philosophical corollary I want to draw from our result, and also a call to arms for this community to contribute to this emerging field at the intersection of machine learning and game theory. Before concluding, I want to give you a tiny bit, some idea about the proof. And in particular, what I wanted to sort of give intuition about is what makes min-max harder than min-min. Okay, why if I had a min-min problem, in particular a minimization problem, I would be able to find local approximate solutions, while when I flip one of the min players to a max player, then all bets are off, as implied by our intractability result. So let me try to give you an impressionistic proof idea. And I'm going to assume some familiarity with sort of the things that take place in PPAD. But, if you are not familiar with those, I still feel that my discussion in the next 7 minutes will give you some good impressionistic idea of what's going on. All right, so the first thing I want to remind you is Sperner's lemma, which is a basic lemma that is used in PAD completeness proofs. So Sperner's lemma says, roughly speaking, that if you color a two-dimensional grid, there are high-dimensional versions, but let's stick with two-dimensional. If you color a two-dimensional grid that's triangulated with 3 colors and you respect this boundary coloring, then no matter how you color the internal vertices of the grid, there must exist at least one trichromatic triangle, and in particular, there has to be an odd number of those. In this picture, here are the 5 trichromatic triangles. Now, proving this theorem, as well as identifying a trichromatic triangle, can be done in a very by running a very simple algorithm, which, however, may take very long if your grid is very large. So that algorithm, what it does, it starts at this bottom left triangle, whose 3 vertices all touch the boundary, and in particular will have this coloring no matter how you color the internal vertices. Right? No matter what you painted, how you paint it here, this triangle will have these colors. And in particular, I know that it has 2 red-yellow doors, this one and this one. And it has exactly 1 red-yellow door that I can use to exit by having yellow on my left, and exactly 1 red-yellow door that I can use to enter it from the outside, in particular having yellow on my left. So what I'm going to do is I'm going to start at this triangle and follow this transition rule. So I'm going to cross a red-yellow door having yellow on my left. And I'm going to keep doing that until, hopefully, and you can prove it will happen, I converge to a trichromatic triangle. Now, the reason this will happen is the following, that, you know, think of my first step, right? So I'm crossing from one triangle to another through a red-yellow door, having yellow on my left. Well, there are 2 cases for the other color. It's either, it can be blue, in which case I found my trichromatic triangle, or it can be yellow or red. In both cases, I will find another yellow door to cross. And you can argue that, so in particular, the only stopping condition for this walk is to hit a trichromatic triangle. And you can argue that, you know, I cannot exit exit this square because there's no red yellow door on the boundary. You can, you know, cross out having yellow on your left. And also you cannot enter into an infinite loop. So you can argue all that. And in fact, you can do something more. You can say, you know, like sort of like using this transition rule, which defines a neighborhood structure between triangles, which is that if they share a red-yellow door, you know, have one point to another if you can cross from one to the other, crossing that door and having yellow on your left. So you can cover your grid with directed paths, directed cycles, and isolated vertices. And you can argue that in this covering, all the endpoints of directed paths are trichromatic except this starting point, which is not, and this is why there is an odd number of trichromatic triangles. So this is a rough idea of what's happening in Sperner. But to argue that min-max equilibrium computation is intractable, in particular PPD complete, what I want to do is I want to reduce Sperner to min-max equilibrium computation. And the way I'm going to do that is I'm going to have a min-max problem, and I'm going to have the Y player choose a triangle. I'm going to have the min player choose an edge, and I'm going to define locally the function value f to depend on whether Y, the triangle player, chose a triangle that has a red-yellow edge, whether X chose a red-yellow edge on that triangle, as well as the orientation of the chosen edge in that triangle. With the goal that the best response dynamics in this min-max problem I'm defining simulate paths of in this directed graph, and which I said earlier can be very long, and this will lead to the intractability. So just to give you a simulation, so here are the here's how it's going to happen with this path that I'm showing you here. So if the triangle player chooses this thing and the edge player chooses that, the function value is +1, which they will then give incentive to the edge player to switch to the other red-yellow edge of that triangle to make the function -1, which will then give incentive to the triangle player to choose to make the function +1, which then will make incentive to the edge player to switch to change it to -1, and this +-1 continue with best response dynamics simulating the paths of the Sperner graph until you arrive at a trichromatic triangle where the edge player has no other red-yellow edge to choose, and that is where the dynamics settle. Now, this is roughly impressionistically how it goes. But the important kind of like, okay, there are less more details, but like the important comment I wanted to make is, why wouldn't I be able to do this type of reduction with a min-min problem? Well, I could, right? So I could have the same type of thing happening where given incentive, making both players a min player and giving them both incentives to change, right? Like I could have kind of like, you know, I could give an incentive to the edge player to switch to that other red yellow edge to make the value from +1 to 0. Then I could give an incentive to the triangle player to change to make it -1. Then give further incentive to the edge player to make it -2, and so on and so forth. And I could keep decreasing the function, you know, to follow the paths of the Sperner graph. But the issue, and that is really the important difference between min-min and min-max. The issue is that I will have to keep decreasing along the path. And the path could be very long in the Sperner instance. So min-min requires memory to maintain a best response trajectory that is very long. While min-max does not need memory. The function value, if you remember, was switching to -1 to +1, -1, +1. You don't need to range, you don't need to remember at which point in the path you're at to be able to implement that strategy. But for a min-min formulation, you would have to maintain memory. And because sort of like in the Sperner instance I started with, you know, the graph is huge and the colors are locally computed by a circuit, you know, I wouldn't want to have this long memory to get an efficient reduction from Sperner to min-max equilibrium computation. So yeah, so I mean, of course, there are a lot of details to implement this strategy. I described it in a discrete space, but it's not. I have to tell you what happens if you're outside of the paths of the Sperner graph. But one of the most kind of like challenging things that we faced here is that sort of like, yeah, like trying to make this discrete function into a continuous one, it has to be ellipsis continuous and smooth. And in high dimensions, this is a very challenging problem. So, you know, it's very challenging to, if I give you kind of like a function value at some vertices of a triangulation, and I ask you to interpolate it so that it is ellipsis and smooth, in high dimensions, this is a very difficult problem. And one of like the big obstacles we faced here, besides kind of like this impressionistic idea we had to reduce Sperner to min-max, the main sort of like challenging thing was to make sure that our function is ellipsis and smooth, and that is a challenging problem there. In any event, this was all at an impressionistic level, and I'm sorry for the digression in the past 10 minutes if that was too abstract. But let me conclude by saying that min-max optimization, equilibrium computation, of course, are intimately related to foundations of game theory, mathematical programming, and online learning theory, as I discussed. And they have found a lot of application in many other fields, okay? As well as recently machine learning. Except we're facing both challenges because of the high dimensionality and the non-convexity of the functions. So what we showed is intractability results for these types of problems that are encountered in machine learning. And that motivates some interesting open questions. One is find asymptotically convergent methods that are not necessarily polynomial time converging in general, non-convex, non-concave settings. And or identify min-max problems which are not convex concave, but nevertheless have extra structure which allows you to compute efficiently min-max equilibria. And we have been working on, you know, stochastic games like Shapley, two-player zero-sum stochastic games, and other generalizations of convex concave domains. But this is pretty much paints the picture of what is going on in this front. Thank you very much, and I'm happy to take questions.
Hi, Kostis, I have a question.
And
yeah, you know, like Goldberg has a recent work on, like, with a few people on this this descent algorithm to be PPID complete. How do you comment on that?
So that's not that's not what they show. So they don't show gradient descent is PPD complete. They show that in some sense, gradient descent is CLS complete, which is, as you know, CLS is a class in the intersection of PPAD and PLS. Yeah. And it is not sort of like for the types of regimes that are of interest to us here in the context of machine learning problems. So, as I said, kind of like, first order methods can arrive at approximate minima in a reasonable number of steps. This is, like, I mean, for a complexity theorist, this is a super polynomial, right? I mean, if your number of rounds is 1 over epsilon, that's not polynomial time. But for practical applications, this is sort of like the type of regime that we are a lot of people care about.
Yeah. Sorry, and let me just ask another question. For page -2 in your PP in your PowerPoint, so do you know this high dimension is in the high dimensional case it's unknown, or when you put it as a challenge there?
Sorry, can you repeat which slide you're talking about?
The last one but one. Like go to last one and move back one.
Okay, hang on a sec. Do you mean this slide? Do you mean, is this slide or this slide?
High dimension, just this last line. When you say high dimensional, it's very challenging. The previous one, sorry. The previous one.
Oh, this one?
The previous page. I haven't seen that page yet. Yeah.
The one with the min-max?
Yeah, this one, min-max, yes. In the last line, you say challenges. Functions need to be ellipses, continuous, and smooth. Smooth means continuous, right? Or it's like, I see.
Yeah.
It means that derivative is continuous, right?
That's right. So the gradient you want, exactly. So to make this reduction ultimately, what you have to do is to have a function that is continuous and has a ellipsis gradient.
That you have already done, right?
We have done it, yeah. So, but I'm illustrating it because it's one of the technical issues, but I think it's a useful tool for more general reductions that you may want to have involving ellipses and smooth functions. So the general statement outside of that, it's a takeaway message that, we provide here is, imagine you define a function on a grid, a high dimensional grid. You define the function values and the gradient values in a high dimensional grid. Then we have a local algorithm that given a point can interpolate your function so that the overall function is ellipsis and smooth. Okay. Right? Which sort of like standard interpolation methods cannot achieve. So like if you do the standard interpolation, like, kind of like partition into simplices and, use the average, the average of the simplex vertices where you belong to interpolate the function value is not going to give you that property. Okay. And it's actually a challenging problem, but there is a tool here, is what I'm saying, that allows you to do that, and you can capitalize on that tool to prove lower bounds for other optimization problems in machine learning.
Okay, yeah, thanks.
Yeah.
Hi, Kostis. I also have a question.
Yeah.
So does the PPAD complete result for the Minimax optimization works for any D, like constant D, like D equal to 2, or like this slide, the D has to be high dimensional, like polynomial in epsilon?
Okay, so we have results for low dimensions as well as high dimensions. Yeah, so I mean, so okay, so here's the point, right? So like in low dimensions, to have a PPT completeness result, so okay, so the result is going to be qualitatively a bit different in low dimensions than high dimensions as a function of epsilon. So
Yeah.
right, so like in low dimensions, if epsilon is a constant, say, then you cannot fit too many triangles in your picture. So you cannot have a intractability results there. Like if epsilon is constant and you are in 3 dimensions, then you can do exhaustive search to find the solution. So we have a PPT completeness result for low dimensions, but epsilon has to be small. It has to be exponentially small. So yeah, so like that's a similar kind of like picture between that we also encountered sort of like back in the day, kind of like in my results and Xiao's results were sort of like like the first results that were shown for PPT completeness, we're talking about exponentially small approximation. And then by to higher dimensional grids, Xiaotia and others extended those results to inverse polynomial in the dimension approximation. So yeah, so you have okay. Just to summarize, yes, there are PPT completeness results in low dimension, but the epsilon there is exponentially small. Yeah.
Yeah, I see. Thank
So,
you.
so it's going to be
Yeah, it's very like
which
the
is
case in
just
Brower.
which is to complement. This is not the regime that is of interest to machine learning. So machine learning is not the intractability result that a machine learning community is interested in. So the intractability result they are interested in is to show that even poly in 1 over epsilon cannot be done. So now if your epsilon is you see what I'm saying. So if epsilon is part of your input and you want to, it's exponentially small, then that's not the type of result that is of relevance to machine learning applications. So that's why we insisted to go to high dimension and can give you intractability results for, epsilons that are inverse poly in the dimension.
Yeah, thank you.
Any other question? If not, I have a couple of questions. Do you think, is there a point of asking smooth complexity type of question beyond worst case type of question here? My guess is that they will extend, basically, right?
You mean as in, yeah, so, I mean, I think in general it is an interesting question. So in particular, I am considering smooth type of questions for several of these these types of questions. For example, just to be so here is something I didn't talk about is some recent work in this, ongoing NeurIPS conference where we study stochastic games. So over there, it certainly does make sense to think about smoothness, right? So, I would probably ask it for in games with structure, and my hope there would be that smooth analysis may take you to even faster algorithms. But yeah,
hard.
Yeah. So on the hardness side, I mean, I haven't very deeply thought about the problem, but I would expect similar type of picture as what we have seen in the past as well as recently for smoothness. That would be. I haven't thought about it deeply. Yeah. My guess would be that these similar intractability results extend the ones we're used to in the normal form setting. But yeah.
So for the SSG, you have a positive result.
Yeah, we're trying. So yeah,
That
give
would
me
be...
give me give me a couple of months.
Okay, that would be awesome. Okay, yeah, I have a few more, but I can ask on offline as well. Like more detail, like what are the structure of the functions and so on. But yeah, I mean, these are related to complexity results somehow.
Yes, I'd be happy to. Yeah, I'd be happy to
Yeah.
talk about it.
Okay, any other question? Okay, so then let's thank Costas for the amazing
Thank you
talk.
very much.
Thank you.
Thank you.
Thank you for giving the talk.